Well, thank you for all coming out this afternoon. I appreciate a platform to speak. My name is Skylar Jordan, and I've been working under Lisa Levy for the summer here at the Autonomy Incubator at NASA Langley. Before I get started, this is just a brief outline of what I'm going to be talking about and some of my work. So I'll do a quick introduction, and then I'll talk about the core of what I did, and then some conclusions about the project and my thoughts about the work for the summer. So just quick about me, I'm a rising senior at the University of Tennessee in Knoxville. I'm studying aerospace engineering, and I'm doing a kind of joint internship between the National Institute of Aerospace and NASA Langley for the summer. And like I said before, I'm working under Lisa Levy. A few years ago, she read this interesting paper called the KSG Power Law paper, and it describes kind of this algorithm for crowd mapping. And so she was very interested in this and its applications or its potential applications for autonomous vehicle pathfinding. So she kind of pitched this to my boss at the NIA as an exploratory research project for me. So here I am. And so our main question is can we apply these crowd mapping algorithms that we've learned about in this paper to autonomous vehicle operations? So kind of a potential application, if you look at this crowd in an airport, what if we have kind of a rover that's stuck in 2 dimensions on the floor and needs to move through this densely crowded area? How can we get this rover to do it safely and intuitively? So our main theory, and I apologize, this slide is kind of text dense, is that we theorize that by applying human crowd mapping algorithms to vehicle pathfinding, we can move with higher efficiency in crowded areas and with improved safety both to humans and the vehicle itself. And so I developed some broad project objectives for what I hope to accomplish over the summer and for what I hope anybody coming to this project after me is able to accomplish. So the first one is we want to research these crowd mapping algorithms, and we want to determine just how feasible it is to actually apply these to vehicles. We don't want to give them to vehicles if they're actually not beneficial. And then the second is we want to test the algorithm application and accuracy with real-world hardware. So we want to put these on the Piglet rovers or actual flying rovers and test how good this actually works. And the main goal is so that we can promote trust in our autonomous systems working in and around crowds. And this will also help for drones to account for more unpredictable human actions. So the first thing I had to do for this project is learn Python. So my college teaches exclusively MATLAB, and we started with the code from the KSG Power Law paper that was written entirely in Python. So it was nice to come into it, and as you can see, Derek was a huge help. Intern Derek was a huge help to my learning and understanding in Python. And I started with the Codecademy and then just jumped in and seemed to go over pretty well. So this is a video of the first code. So the KSG Power Law paper came with a pre-written code that would generate this simulation environment. So these circles all represent what we call agents, what the paper describes as agents and what the code describes as agents. So you can think of these as our models of humans, but also as our models of how autonomous vehicles would be working in and around humans. So you could think of any individual one of these circles as humans. So this is a video running of what this algorithm does. So it spawns in these circles with random goal velocities. So this, I don't know how well you can see it, but the green vector is what the agent is trying to accomplish with its red vector. And so this is good and bad. So we have some pros and cons with this simulation. So the pros are that this algorithm proves that we can have a densely populated area and be able to control and predict the movements of drones and or humans. There are very few collisions, if any happen ever. And this really provides a good starting platform for what we're trying to do with its application to drones. It does have a lot of problems, though. So the simulation environment here is not customizable. So if we're trying to use this algorithm to give drones instructions on how to move, this simulation is just spawning in things randomly, and they really have no goal about what they're doing. And the main problem with that is that it's incentivized by a goal velocity. I as a human, don't plan where I'm going by saying I want to go in that direction with that velocity. I'm trying to meet a goal position. So we needed to fix that. There's no fix or nothing that the code will do when two agents overlap, which is a big problem because we don't want agents overlapping. We don't want humans crashing into each other. We don't want drones crashing into humans or drones crashing into other drones. The code was also very poorly commented, which was a big problem in my learning of Python. So to start off with my edits, I added a goal position defined. So instead of going off the screen randomly, these agents are now attempting to find their way to a goal position. And we were doing this by marking a spot in our simulation environment, and then the agent's goal velocity then updates with every iteration of the simulation to point to that spot now. And this doesn't hurt its algorithm when trying to plan around other things. So you can watch this video and see that each agent is trying to make its way to the opposite side of the simulation environment. They don't run into each other, and they all go where they're going. In the original thing, they would have all just ran off, and I wouldn't have even been able to define a starting position for them. The next thing I did was I added waypoints. So we can now tell an agent where to start, where to go, and then once you achieve that position, where you can go next. I also did a very preliminary research into grouping. It's not great. It works well in straight lines, as you'll see in this simulation, but when this agent tries to turn around, it gets a little messy. But Lisa and I were actually talking earlier today, and it really shows that there is a lot of research potential in this field of grouping and how humans move in groups, and can we apply that to drone operation as well. So you'll see here the red one is acting as the leader, and the yellow agent is acting as the follower. So it works pretty well in a straight line, but once it hits the next position, it gets a little messy. And then this one demonstrates the overlapping problem fix that I made. So the overlapping typically happens when all of these agents are trying to go to the same position. And that's not good. They'll end up trying to overlap each other and kind of eat each other, which is bad because then our drones are running into each other and our drones are running into other humans. So what I did is when you detect an overlap, both agents that are overlapping get bumped back. So if you watch this guy right here, sorry, that guy right there, he's going to hit that guy, and then they're both going to bump back. Just like that. It's really simple, but really important. So we then wanted to compare this simulation to how people move in real life. So I found this stock video online of these people moving, and they're kind of steering around into each other. And then I made a mock simulation in our simulation environment using these crowd mapping algorithms. So I think if I play both of these at the same time, so if you watch these three guys right here, that's these three guys here, and those two guys are those two guys. So it shows that they don't model it exactly, but it's close. And it's close enough to where the research in this should continue. But that gets us into the real testing and approach. So I have not been able to run any actual simulations using the Vicon system yet due to slowdowns with the move and everything. I think with one more week here, I would have gotten it, but I do have a code ready to run. It's untested. But my theory behind this and kind of my idea of how this would work is that we can establish the DDS and Vicon connection. We can update the rover position in our simulation environment. Then we can run a simulation for about 10 iterations, and then pull that new position of where all the rovers are, and then send that in a waypoint through Matt's waypoint finder code back, and then the rovers will drive to the new position, and then we just reiterate again. So is this application feasible? So this is the main question that we've been asking since the beginning. So what I've determined is that it's really promising. It's really interesting. It's a really interesting field, and there's a lot of research avenues that can happen here. The main thing is it really requires further research and development, either in the AI or by another third party. And what really needs to be done is I feel that I've gotten it to the point where it's really ready for actual hardware testing. And unfortunately, again, I was not able to perform the hardware testing myself, but it's really ready for it. And so testing on piglet drones or even flying applications and with humans, it should all be ready for that. Some other considerations for this is that these CRAD simulations are accurate. It works when there's a big group of people, but when there are smaller simulations with people moving head-to-head or just a few drones operating, it doesn't become as intuitive as it should be for humans predicting it. So my idea is we can kind of code in these road rules. So in America, when we approach each other in a head-to-head situation in a hallway, we both move to the right. In other countries, you might move to the left, and there are other situations. So it'd be interesting to read into some studies about this and apply it back into this algorithm, just to make the whole thing more rigid. But so these agents are pretty inclined to change their velocity rather than a trajectory. And again, Lisa and I were having a discussion about this earlier, and there are some situations in which people interacting with each other are more inclined to change their trajectory or velocity. So it's interesting. So if I round a corner and somebody else is rounding the same corner, we both would stop, or rather than change of velocity when we have more knowledge about our environment. So my idea is we can incentivize these agents on a case-to-case case-to-case basis on when they should be preserving energy and not preserving energy. And a weird bug that's now a feature, I guess, is in agents with a large radius in the simulation will yield to agents with smaller radiuses. And I have no idea why this happens. And I've spent a lot of time scratching my head trying to figure it out. And I have no idea. So if anybody wants to take a look, then I'd love to know why that happens. But again, since I wasn't able to continue on to the real hardware testing, I've created fairly thorough documentation on how to use the simulation environment and then how I think it should be implemented into real hardware testing. So I've created 4 unique simulations in the code that's accompanied with the actual documentation for how to create single agent travel, a single agent with waypoints, multiple agents going head-to-head, and then 8 agents with a common goal position, just to demonstrate what the capabilities of the simulation environment are. I've also thoroughly commented the whole code now because the original researchers didn't do that for some reason. And so, yeah, and again, I really think that it's ready for actual hardware testing. But that wraps up my presentation for now. I really want to make a point to thank a few people in specific. Matt from downstairs has been a great help and very, very patient with me for my questions about Vicon and DDS, and I think it's to the point where he tries to run away from me now when I go to ask him questions, but he's been a great help and very tolerant with me. Also, Derek, intern Derek, probably deserves about as much credit on this project as I do for his help with me and my troubles with learning Python. Also, both Becky and Lisa, thank you so much for giving me the opportunity to come over here and mentor me and help me for where I'm trying to go. And again, thank you, Danette, for allowing me to come and distract your employees for the last 5 weeks. So with that, I'll open it up to questions.
So in the context of UAS, what do you think, or how do you think you could apply this? Like, there are many ways you could apply this algorithm. What is the one that...
Right. So it's important to note that I don't think that every drone operating should have this kind of algorithm applied. It's specifically for drones that are operating in and around humans. And so in very crowded situations like malls or airports, if we have either flying or ground-based autonomous vehicle platforms that are working in and around humans, either for something like package delivery or some sorts of communication networks, then they need to be able to work around humans safely, and they need to be intuitive enough for humans to understand what they're doing. And the idea is that if we can make them, so to us, to humans, other humans, it's intuitive to know what they're doing. And so we kind of want to make drones the same way. So just basically applications for close proximity operation to other humans.
So do you think you could modify this algorithm so we can simulate how a crowd would behave when a UAS approaches?
Yeah, so I've actually done tests with that here. And I used the bug, which is now a feature of the large radius yielding to the smaller radius. And I took a small radius that I would assume is a rover, and I would push it, or I'd manually control it to go through a crowd of large radius, and they would all move out of the way. And it still follows the algorithm. So it is interesting. So this algorithm definitely can do it. It might need some additional modifications to make it more accurate in testing, for sure. But I actually have done testing like that.
So first of all, kudos to referring to a bug as a feature.
Yeah.
You're well on your way to becoming a computer scientist.
Yeah.
So you talked about this. Works better with large crowds,
Mm-hmm.
right? Smaller, by smaller simulations you mean fewer agents.
Exactly,
right?
yeah.
Or less accurate. Any intuition about why that is?
It's every simulation that the code runs, it has some degree of randomness in it. So if you put two facing right at each other, they will not always go the same way around each other. But I think that it's important for us to make it more so that they do in some applications, based on like cultural, for which side of the road do you drive on. But intuition as to why it does that, I think...
Why would you see this with a fewer number of agents, and it sounds like it's a little more predictable or accurate, you say here, when there's a large number of agents.
Right.
Any thoughts on that?
I think it just comes from the algorithm was developed to model large amounts of humans rather than smaller one-on-one interactions. So
Do you think it could have anything to do with the increased constraints that come with a large number of people in a confined space versus a smaller number of people in a confined space? You have fewer options if it's very, very crowded.
right. It's definitely possible. It still works with small groups. It just seems like it's more intuitive for a human to predict where one agent in specific is going in a larger group.
When you say it works, do you mean that it is following what you see happening with real humans? Is that what you mean? Like it matches like a video, for example?
Yeah, it's close. And nothing's going to match perfectly because every single human moves differently based on a number of different reasons. But yeah.
So that was one of the comments that I had made to him when we were showing the video, and he kind of wanted it to match exactly to what we saw in the video. And I said, but wait, what we're missing is the fact that the circles moving is intuitive, is understandable by us. Just watching it, saying, okay, yeah, those are people walking in a crowd. If you put those exact motions on that crowd, you would have just been like, of course, those are people walking. That's how we move. And there's a part in there where there's three together, and as one agent starts to kind of encroach, the one on the left tucks behind. And we do it all the time when we're walking against each other as crowds.
I would argue that you mentioned that you would want the same result every time if you ran it. I would argue that real humans don't do that. It's not the same every time that you want the stochastic.
Yeah, to clarify, you want the same result in times where the majority of people would predict the situation happening in one way. Like a head-to-head, like if we were to ask all of you, for two people moving head-to-head, which way are they going to go around each other?
But
That's
it's
the
totally like, even with real humans, right? Like, it literally depends on the two humans. It depends on what's around the two humans. Like, I don't think there is one right answer necessarily. And
Yeah.
I think that's why the algorithm is stochastic in that way.
Yeah.
Because, like, that is more realistic, I think.
Yeah, that was just my intuition, just thinking specifically about the head-to-head. But you're absolutely right in that, and that's what's kind of interesting about the algorithm is it's a little random. So.
Can you go back to your video and narrate, point to things? What are we seeing?
So these three agents are going to be a group of three agents that come in from the bottom here and move up. There are another two agents that are modeling two people coming down on the screen there. And then there's another two agents that model a group that's coming in from the side here. And so when you play them side by side, you can see this one's a little ahead there, but you can see they move up and then everything goes like that. So again, it's not perfect, but it doesn't have to be. It shows that there is still randomness in the simulation. So.
Another point is that if you're a human and you see a thing rushing at
Yeah.
you will probably not be familiar with the rules of the road that it's following.
And that's why, yeah, that's why I was saying it could be done on a cultural basis. So but there would need to be studies into what is common for people to use.
So
but
humans use, and Skylar and I have talked about
yeah.
that humans use eye contact. If I make eye contact with someone, I know that we at least understand we're not going to hit each other. But if someone's on their phone, then I give them a wider berth. And so there's all these like
So this
humanisms.
requires
There's-
a much wider berth.
Yeah.
Well, and so that's one of the things that
You can change
using
radius. Yeah.
smaller-
Mhm.
Which might just
Circles.
obviate the need to do this. Then you just, carry something in a corridor and make loud sounds so
Make
people
sounds.
don't run.
Like bears, so
Yeah,
they're trying to scare.
that's it.
Okay. No. So I had one final question.
Yeah.
And that is, I know you're going back to school for your senior year and everything, and you have kind of a path that you're looking at. Did working with Python and working kind of in this kind of simulation and change any of your thoughts about going forward, or what your path is, or help define better some things that you already thought that you may want to do or will be doing?
Yeah. So for sure. So I think I was telling you earlier that at the beginning the project sounded interesting, but I was like, it's not specifically what I'm looking into doing. But I'll do it because it's a job at NASA, I guess. So, why wouldn't you do it? So, but after really diving into it, it's very interesting, and it really shows you that there are a lot more human factors that go into this kind of engineering work than you would think initially. And so specifically for me, I've found that I really enjoy going from coding on the computer and then going towards an actual hardware test and kind of back and forth kind of iterative design process. So I found that I've really enjoyed that.